attach a cable lug to it, and we have a red cube plug with a crimp terminal where you can crimp a cable on it and put it in and out only by plugging the terminal to the red cube plug. There's also an red cube THR and SMD component, but the topic for today will be the press fit elements. Here you can see how it works. Our red cube terminals are solderless. There is a real cold weld. This real cold weld is gas tight, and it has a high mechanical and electrical reliability. The terminal itself is made out of brass with a thin layer on it, and the pin diameter is slightly larger than the copper via in the PCB. The principle of assembly is that the element will be pressed into the PCB, and this creates the cold welding effect between the pin and the via. It's not allowed to solder them after insertion. The connection is already secure, and it's important to avoid rapid heating because it can damage your PCB. The connection itself is gas tight. In the connection can not join any molecules that can oxidate the connection and break it. And like I said before, the cold welding ensures a high mechanical and electrical bond. The resistance, the electrical resistance for these connections is even lower than any soldered connections. So there is no need to solder it after press in. We can verify a red cube press fit connection after insertion by pulling it out. We can measure the extraction force per pin to get an idea of the quality. We do it in this way. It's like a destructive test. It's also a need for our customers. When you have any problems, you can send your PCB and we can check it, but it's a destructive test. And we can see here that we will get a force of round about 100 Newton per pin extraction force. So that means for a terminal with 12 pins, we will get 120 Newton as force as all to extract it from the PCB. But it depends on the PCB thickness, the hole precision, and the surface finish and the coating technology. The graph here at the right side is for a PCB with a thickness of 1.6 millimeter, and you can see the extraction force increases linear until the red cube press fit terminal breaks out of the PCB. What you have to take care for in your design is that you drill the right hole diameter, use the right copper thickness and the right surface, but we will discuss it in detail now. You can see here on the left side the drill hole in your PCB with a diameter of 1.6 millimeter, and the pin of the red cube has a diagonal in an equal size. And after the drill hole, there is a copper plating to the via. The optimal range of the thickness of the copper will be 30 to 40 micrometer. The more copper will be, the more harder will the press-in process. And the important thing will be that after the plating with copper, the via hole diameter is slightly below 1.6 millimeters to ensure that the red cube pin enters by force into the copper. Only with that there will be a cold welding between the red cube pin and the PCB copper. and only that will ensure the high reliability for the mechanical and electrical connection. On top of the copper, there will be a last layer for the chemical thin. For example, there will be a thin layer of 2 micrometer. The maximum layer thickness for the thin will be 15 micrometers, and so you will get a hole diameter of 1.475 millimeters. And the thin will protect the copper from corrosion and will ensure that you get a reliable copper-to-copper contact after the press-in. Here we can see a cross-section of the right side of a red cube press fit pin. At the top right here you can see the pin itself with the tin layer and the brass material, and here you can see the copper of the via, and all around here will be the FR4. And what you can see at the right upper side, that the via copper is deformed from the red cube pin, and the FR4 is not broken. It's deformed by the copper of the via, but it's intact. The tin will be displaced during the press-in process and will form chips, which is altering the surface. And the mechanical and electrical integrity only guaranteed after continuous insertion process. That means there is no second insertion possible. When you do it, you will damage the via and compromise the electrical contact, and you will prevent proper cold welding. Here's another cross-section where you can see the copper around the via. The red cube pin is pressed in directly into the copper here. The tin layer from the via and from the pin are removed, and so we will get a cold weld between the brass and the copper of the via. And the gray area here between the press fit pin and the via is in resin. Normally that's not there, that will be air, but we need it for the cross section. You can see here the angle of the connection between the pin and the via, and when we measure it, it will be around about 10 to 15 degree, but 3 degree will already be enough to have a high mechanical and electrical reliability. What we have done here is an imperial measurement of the press in force in Newton per pin, and we have prepared a small example for a PCB with a thickness of 3.2 millimeter, and we have a PCB with a surface finish of chemical thin, and we decided to choose a layout for the hole diametry for the finished via with the plating of 1.476 millimeters, and so we have here this column where we can see that the insertion force for one pin will be between 140 and 340 Newton per pin, and when we calculate that, we will get 1.7 kilonewton for the lowest and 4 kilonewton for the highest value of the force. But take care, it's safe to add a security margin of 20%, and so we will get a maximum press-in force of 5 kilonewton. That can easily be done with a press by hand or also with an automatic press when you have a high volume of red cubes to press in. Here are some important informations to the press-in process itself and the optical inspection after the press-in process. What you need is a press, you need the stamp, you need to support the PCB itself, and you need the terminal. It's very important that the press-in process will be done in one single step with a feed rate from 100 to 250 millimeter per minute. And to ensure the small gap here with 0.1 millimeter, it's important to adjust the end stop of the press. The small gap here is important to take care that at the end of the press-in process, not the whole press force will be applied to the PCB, because that will break the via holes and the FR4, and over time the PCB will be delaminate and break. And only with the gap you can ensure that the press process ends before the force will be applied to the PCB. And there is one second thing to control, to take care that you can use and apply the complete current and use the maximum electrical performance. It's best to look for the chamfer at the red cube pin. It should look out of the bottom of the PCB, and so you can be sure that all layers and also the bottom layer of copper will be connected to the red cube pin. We also have another solderless connector. It's called the SKEDD connector. Unlike the press fit technology, the SKEDD connector does not deform the plated through hole permanently. Instead, the SKEDD forks are elastic preloaded and return to their original shape after disconnection. That means this kind of connector can connect it multiple times. We have for the SKEDD 2.54 millimeter two layouts, the debugging and the permanent layout. The debugging layout has 50 mating cycles and the permanent layout 10 mating cycles. And soon there will be another connector which depends on that connect technology. You can see it here. And it's a connector with only one side on the wire and layout in the PCB. Now we want to look for the high frequency challenges we have on our PCBs. For that we have for example, the SMR PCB connectors in our portfolio. You can see it here on the left side. We have different types, the THT, SMD, hybrid, solderless, and end launch types. We also have a tool to apply the right torque for mounting the SMA connectors, so we don't damage the connector and the PCB itself. We have a lot of adapters like jack, plug, jack, plug, and I like them because I use them very often for my measurement units. So I don't want to damage the threads of my measurement units. I will damage the adapter instead. And this is, I think, a very nice tool. To get the maximum performance of all of the connectors, it's very easy to select a mating cable for it. We have flexible and also hand formable cables, but you can see it on our website and support you with the cable selector. What challenges we have to match the impedance of an PCB trace to an connector, like an SMR connector. We can see it here on the left side. The pin of the SMR connectors have to be matched to the signal trace to ensure the impedance. It shouldn't change too dramatically. For such impedance match, and so-called line taper could be used for the trace itself, and also an GND taper for the reference plane on the top layer. And it's best when you have a multi-layer board to use the defected ground structure like shown here, but we will talk about this in more detail now. Here we have an example for an matching impedance from 50 ohm to 25 ohm. Sometimes customer want to change the impedance of the 50 ohm connector to, for example, 74 or 75 ohms, or also 25 ohms. Our example today will be 25 ohms, and we will see that we have a normal layout for it and an optimized layout for it, and we will show you the measurement results for both of these layouts. For this line taper, this is a geometry modification of a transmission line typically used as SMA interfaces. The purpose is to correct the impedance mismatch caused by capacitive effects from nearby structures like the SMR pin, for example. The transition areas behaves like a coplanar waveguide with ground. The gap between the signal and the ground influences the local impedance. We will see it later. The taper shape should be smoothed and curved and optimized for signal losses during transition, and the form is not just curved, it's frequency dependent. The curved taper can be divided into multiple squares. We can see it here. There are a lot of them, and the ideal size is a quarter of the wavelength or multiples of the quarter of the wavelength, and that shows the minimal signal loss and prevents constructive and deconstructive undesired wave interferences. The line taper design we can see here on the left side was derived from simulation data. Before we created the test PCB, we performed detailed calculations and simulations to determine the optimal geometry. So the answer to the classic question, which came first, the chicken or the egg? In this case, it was the simulation data. Based on the results of the simulation data, we developed the layout and fabricated the test boards for it. The image already shows the complexity of the linear tape structure, which had to be carefully recreated in Altium Designer. For this, we use the DXF importing function from Altium Designer, and so we can transfer the geometry to Altium Designer. On the left side, you can see the schematic for the components we used. It was an SMR connector flat tap with THT grounding pins. And in the middle, we have the layout according to the data sheet. And at the right side, we have a modified layout with a line taper we have still talked about. And we added a second via on each pin for the ground. Here you can see the PCB design for the two layouts, or the top of the PCB here we have the default layout from the datasheet, and below this we have the optimized layout with the line taper. We can see it here and here, and so we have a 50 ohm system for the SMR connectors at left and right, and we change the impedance for the signal trace to 25 ohm, and we want to achieve that we have as less as signal losses as possible. Below here you can see the stack up of the board. It's a simple 2-layer stack up with core and top and bottom copper foil, and it's a normal FR4. As in connector, I already said we used an THT and launch flat type. And here you can see the results from the measurement about the frequency at the x-axis and the insertion loss in dB at the y-axis, and in red you can see the datasheet layout, which has already a higher signal loss at 6 GHz, and where the modified layout is still a little bit better. And you can see here that we have moved the insertion loss more to the right, to the higher frequencies, and so we can use this connector for the LTE band and the Bluetooth and the Wi-Fi radio protocols. Here we can see a second application which we have modified. It's also an SMA connector, and what we can see here is that there is no ground plane between the GND pins and the edge of the PCB, and so we will get a so-called slot antenna, but it can be avoided when we add an reference plane to the GND pins of the SMR connector, and it's also possible to remove the slot antenna completely when we solder the slot here with solder paste. Here we have the results also about frequency and the insertion loss with the soldered and removed slot antenna. In red also the datasheet layout, and in gray the modified layout, and we can see that there will be no more insertion loss with the in case of the slot antenna effect. For both layouts we have measured the voltage standing wave ratio, which we can see here. And what we can see here is that only for the frequency range between 9 to 14 GHz, the datasheet layout performs a slightly bit better, but at all the modified layout is best choice for frequency from DC up to 80 GHz, and in the range from 9 to 14 GHz, the voltage standing ratio is smaller than 1.5. That means we will always get around about 70% of our signal. To get best of our connectors, it would also be nice that you can choose the cables from our website with our cable connectors depending on your needs of your application. You can see here at the top the frequency as a parameter and the nominal outer diameter and the minimum bending radius and the operating temperature range. So it's easy with the cable selector, you find your right cable. After we have talked about high currents, frequencies, and how to deal with them of the PCB, it's time to look about the voltage we apply to our connectors and what happens if we don't take care about. I think everybody knows what we can see here. There is a thunderstorm with a lightning, and I hope that you agree to me that should be avoided for any PCB design. And how we can do that, we have to take care about clearance and cribbages, and so we want to talk about what are the basics. Here we have a PCB with two conductive parts, and there is air between, and we have here the clearance as distance between these both objects in the air, and there is also the cribbage distance, which is the distance on the surface between two conductive parts. And here we can see that both distances, clearance and cribbages, are the same. For the other three cases here, we can see what happens. We add a small slot in the surface of the PCB, and now we can see that the clearance will be the same from the two conductive parts. It's the distance over the air, and the creepage, the leakage current, will travel or will use the path along the surface of the PCB, and it looks like the blue line. But what happens when the slot is not wide enough? We can see it here. Clearance and creepage distance will also be the same. And there is another possibility. When we cut a groove into our PCB, we can see that the creepage won't change, but the clearance will travel along the surface of the PCB. And when the width of the slot becomes too small, it will also jump over it and go ahead here. For clearance distances above 3 millimeter, we can see here the dimensions of X for the slots and the groove in the table depending on the pollution degree. We will see later what the pollution degree means. Here we can see how to increase the creepage distance. For example, for a terminal block, we can add a small cutout here to the PCB, and when we take care that the cutout or the slot is wide enough, we will see that the creepage will travel along the surface of the PCB and travel around the slot. The clearance is also the air-to-air distance between the two conductors, and so it's only a straight line in red. Here on this PCB, we can see exactly what we have seen on the right top. There is a terminal block, and between the two pins there is a cutout to ensure the creepage distance. And also here between the transformer, we can see there is a cutout in the PCB between the primary and the secondary side of the transformer pins. So the creepage is also increased. Here is another example how to increase creepage and clearance distance. Now we have added an insulator material which is placed vertically in a slot, and we can see that the clearance will be no more the direct path from the two conductive parts. Now the air-to-air distance is above the insulating material and on the other side down to the conductive part. And the creepage we can see here follows the surface of the PCB and underneath the insulator material to the right side of the conductive part. We can see it here. There are two red tubes on the PCB, and now we have the clearance will go around the insulator material, and the creepage will the path below the insulator material. But we can also see that the clearance will be longer. The clearance path is longer than the creepage path. It's possible to increase it when we use here some glue to take care that the creepage will travel around the insulator material and use the longer path and not below the insulator material. Here we have an USB type 1 THT, and we will see a breakdown of the connector. You can see the arc between the pin 1 and the pin 2 of the THT USB 2 type A connector, and after the arc you can see here a small carbonized path between the two pins, but it doesn't burn. But the electrical function for this connector will be no more given. And what we have tested is the breakdown voltage. The data sheet is 500 volt per minute, and we measured 1000 volts. So for the connectors will be a big security margin. You can see the operating voltage for this part is 30 volts. The breakdown voltage in the data sheet is 500 volts per minute, and it was measured with 1000 volts. At the end, we will see how the clearance and creepages, on what will it depend. The clearance distance is depending on the pollution degree, the altitude, the over voltage category, the impulse withstand voltage, and the working voltage. And the creepage distance depends on pollution degree, insulator, cooperative tracking index, the over voltage category, and the working voltage. That means if you have clearance problems, it doesn't help to change the insulator material with the comparative tracking index, short CTI. You have to look for another solution. And on the other hand, if you have determined the creepage distance for your application, it doesn't matter if you change the altitude, over voltage category, or the impulse withstand voltage. With the next topic, you can see here we're getting closer and closer to the mechanical changes of our PCB connectors. And here we have a small electrical device with an DC jack inside it. And now I want to show you what you can do to increase the push-pull force for such a connector. So you can use it as SMD component and no more as THT component when you need, for example, to reduce your assembly costs and remove the THT solder process. So we have here a layout for a THT DC power jack. It's the original datasheet layout, and on the right side here you can see the placement on the PCB as 3D model. And compared to this, we also have the original datasheet layout for the SMD component, and on the right side also the 3D model for it. Then we have modified the layout. We have decided to check two types of modifications. The one modification will be the Mickey Mouse layout. You can see it here on the left side, and on the right side we have 4 vias at each side of the SMD pad with 4 connections going through the vias. Here you can see the PCB. Here we have 2 THT components. At the right top side we have the SMD component with the modified layout in the Mickey Mouse style, and below this we have the layout with the 4 vias on each side of the pad. And we have tested the push and pull force with a compression testing machine, which acts like the user to push the connector in, and also the pull on the cable or at the connector to show what will happen and measure the forces for that. In the left side you can see here the mounting plate, which is fixed to the vise, and the PCB is mounted to the mounting plate, and above that we have here the punch, which will compress the connector. And here you can see the pull test, the mounting plate with the PCB connector and the punch, and we can see that we can pull in the Z-axis and also in the Y-axis. The result of the measurement of the push-pull test can be seen here in that table. What we can see is that the THT datasheet layout has really high push and pull force. That means round about 75 kilograms as push force and round about 50 kilograms as pull force. That means you can put in the connector with round about 75 kilograms without destroying it, and pulling at the cable with around about 50 kilograms. And compared to this, we have the standard datasheet layout. We get 20 kilograms for the push in and only 11 kilograms for pulling at the cable. For the Mickey Mouse layout, we get a push force of around about 37 kilograms and 220 kilograms for the pull force. The SMT layout with the 4 vias is nearly the same like the Mickey Mouse layout, but the Mickey Mouse layout is more easy. You do not need any vias. You can attach other components at the bottom side, and you don't have to take care that your solder paste will flow through the vias from the pads of the SMD component. And there is another interesting test we have done. We have glued the SMT component on both sides, and then we have looked what happens when we pulled on it, and we can see here that the glue will break at 60 kilograms, and that is only that what you can see. Before that, round about with 30 kilograms, the first and the second solder joint is still broken before the glue breaks. And at last topic, I want to show you an easy multi-board design with Altium Designer and how we support that. You can see here 3 PCBs. All these PCBs include a lot of 3D models and also the schematic symbols and footprints and 3D models and spice models, and you can also get S parameters on request. All this stuff will be combined on our platform support page and will be available there. And you can look which platforms we will support in future there and how it is going on. And now we will assemble the boards together. I will show it to you. The motherboard here you can see is from our FAE ICANN kit, and also these 2 PCBs are also from our FAE ICANN kit. We use them on customer side to support the design in process with our terminal management interface products. And here we can see how easy it is to make them together. We only have to decide on which axis we want to mate the 2 PCBs. I choose here the SMT spacer and the lamellar basket connector to mate the 2 boards together. And now we can see that they will mate together. We can see here all 3 boards, they are mated together. And I think it looks really great, and it looks like that everything is done. But be sure you have to take care that all the models are only with nominal dimensions. There are no tolerances, and it's up to you to keep an eye on your tolerances. So I hope you enjoyed the webinar, and if you have got any questions, don't be shy and ask me. So I wish you a nice ongoing summit. See you soon. Bye-bye.
All right. Well, thank you, Renee, for that really detailed presentation on PCB design. It can often be so difficult to find good educational resources on many of those topics you covered, just not kind of in the mainstream of PCB design discussions. So thank you again. As we wrap up our last All About PCBs live session of the day, I'd like you to announce our prize winners. First, our session prize winners are Jeff Smith and Frank Islis. We'll be in touch with you within the next week to ensure we have the information we need to send you those All About Circuits goodies. And since this is our last session of the day, I get to announce today's grand prize winner. Jacob Herbold, you are our lucky grand prize winner. Our All About Circuits event team will be reaching out so that you can select a prize you truly want. And the All About Circuit Summit series will be continuing every Wednesday during the month of October. We hope to see you again next week for All About Embedded and Edge Computing. In a moment, you will be redirected to Worth Electronics Summit Series microsite. I encourage you to check out the other live sessions, the keynotes, and published content there. Thank you, everyone, for attending All About Circuit Summit Series 2025.